All right, let's talk our way through sections 4 and 5 of the textbook in chapter 2. And so, if you remember last video, we ended by talking about the law of conservation of energy. And so here we're going to extend that a little bit further. There's two other laws at work, the two laws of thermodynamics, which basically talk about that in a little more specificity. So the first law of thermodynamics, we cannot create or destroy energy. Now we talked about matter before. Energy, it's basically the same ideology that we're using in both cases. So the law of conservation of energy can't create or destroy energy. Whatever energy the universe started with is the amount of energy the universe is going to end with. Okay? It always equals input of energy, always equals output of energy. Okay? So it's a straightforward law. Now the law of thermodynamics, the second law here, is a little bit different. Energy quality is always decreasing. So the energy total is always staying the same, but in Law 2, we talk about a decrease, and the key here is the quality of the energy. So some energy is in a form that we can use, and there's other forms of energy that aren't as useful to humans, to the planet, to whatever. And so second law of conservation of energy basically says that the amount of usable energy in the universe is going down or diminishing over time. It degrades. So you need to know those two laws. And as a result, it's a good thing that we constantly get input of solar energy from the sun. Because if we didn't, the energy we'd have on the planet without the sun would slowly degrade and become less and less useful for us as waste energy and heat and all of those other things. And so the sun constantly provides energy for us. Some of that energy goes into photosynthesis, and then it turns into something that we can use down the line. Some of it gets wasted as heat. Move on. Some of that energy then gets eaten, or some of that energy or chemical energy from plants gets eaten as food. It's food energy. Some of it's lost to waste. That food energy then gets transferred into mechanical or making us move and run around. And so when that happens, wasted energy again. And so you can see that energy gets pulled out of the system every time it gets transferred to a different form. And so as that happens, if we didn't have constant input of solar energy into the system, we would slowly run out of energy on the planet. And so handy that the sun's up there, I guess. Section 5 in your book. This is talking about flows and movements, processes within a system. And so the first thing you need to know here is these two terms. These two terms are important for you. Positive feedback loops and negative feedback loops. So when we're talking about matter and energy and information and it's working its way through the system, it can cause a system to do more, or it could cause a system to do less than what it was doing before, or in the context of what it is doing. And so a positive feedback loop, positive means more. Okay? Positive means you're going to add to it. So it causes a change further in the direction that the initial thing was causing. Negative stops that process from happening. And they have two examples here, and there's a picture of it on the next page for you. So examples, soil erosion. When we take away soil and we erode it away, we lose the vegetation in the area. The next time it floods, that will cause greater erosion. So by creating initial soil erosion, you'll create further and further soil erosions to occur. That would be an example of a positive feedback loop, where one course of action causes a greater amount in that course of action. Negative feedback loops do the opposite, and a great example of that is the furnace at your house. You turn the furnace on at your house, set it to 72 degrees, the furnace will kick on and heat up to 72 degrees, and then it will shut itself off when it gets to that temperature. So you see that the opposite is happening. It's corrective, as it says here. Once it gets to the temperature it needs, turns off, it'll stay there until it cools back down, then it'll turn itself back on again. So there's an example of a negative. And so if you look on this page, those two things are being shown here in this illustration. If you cause erosion or removing of vegetation, you'll create soil erosion. That soil erosion will lead to more and more soil erosion and greater wearing away. Grand Canyon, for instance. And then the furnace example, where one is turning into the other, is right here. Okay, where we have a warm house, heats up to 70, tells it to shut off, cools back down, heats back up. Negative feedback loop. Okay, so Within that process, we have all of these interactions that are occurring, positive and negative feedback loops, all that kind of stuff. But the important thing is, within these complex systems, is sometimes that feedback stimulus, either positive or negative, may very well have a time delay on it. So the furnace in your house interacts pretty quickly, within a matter of minutes. It adjusts itself, and you know that it might go over 70 degrees by 2 degrees, but it catches on and shuts itself off. Other systems, the time delay is much greater. You might be doing an action now that you won't see the results of for 10, 15, 20, 30 years. And that's when we talk about environmental science, the big thing we're talking about now is global warming. That is the argument for fixing global warming right now, is we're doing things now to the planet that may very well affect it in the future, and that's the argument that happens. And sometimes that feedback time delay is so long that we might reach what they call the threshold or the tipping point of a system, where the system will fundamentally shift, where you can't go back after you get to that point. So if the time delay is, say, for global warming, gets to a point where it's going to cause a global shift based on certain temperatures being reached, maybe the things that are causing it we're pumping into the system now, but we won't see the result of those until later. We may very well already be past the tipping point of the threshold, and it's just a matter of time before it shows up and creates something that can't be reversed or corrected. So those are examples of thresholds or tipping points. There's lots of them within environmental science. The global warming one is the hotbed topic. The last idea from this chapter that you really should soak in is synergistic interaction. And so when we do stuff, there is some type of result that occurs. And so, for instance, I'll give you an example. If you say are exposed to asbestos, it's really hard on your lungs, right? That's the example down here. Okay? And so it will cause lung cancer in the long run. If I'm smoking, it can also cause lung cancer in the long run. But if I do both of those two things together, asbestos, I don't get the effects of smoking plus the effects of asbestos, as in 2 + 2 = 4. Synergistic interaction says that if I have the effect of smoking of 2 and I have the effect of asbestos of 2, the resulting chance of lung cancer isn't 4, it could be 6 or 8 or 10. So the combination of the two amplifies the result above what the sum of the pieces is. Okay? So those are the main ideas that I would like to talk about from chapter 2. Make sure you guys get your reading done and your notes taken care of for me. Thanks. Bye.